Hello, and welcome to Level 3 of Understanding the Fourier Transform. This is going to be the most in-depth and the most math-heavy explanation of the Fourier Transform, and we're going to work upon the ideas that we came up in Level 1 and Level 2. So we're going to start off right away with the definition of the Fourier Transform that we came up with, or that we saw in Level 2. And it's f of omega is equal to the integral from minus infinity to infinity of e to the minus I omega t times f of t dt. And so, using what we learned in the past videos, we can break this down. This f of t is really our signal that we're plotting in time, and then e to the minus I omega t just plots a wave of angular frequency omega over that signal, and then we multiply them and then add up all the points, i.e. integrate across all of time. And we know if e to the minus I omega t, which just for now just plots the wave over top, if that's strongly correlated with f of t, it means that the multiplication will be positive, so you're adding up a bunch of positive numbers, which makes this f of omega positive. And that's the level 2 understanding that we have. But I want to get into why we use e to the minus I omega t, because it turns out it's necessary. You can't just use a sign. A sign will give you the wrong answer. And it turns out this actually is a key component. This e to the minus I omega t gives you the phase and it gives you the amplitude. And I want to explain how that happens. So first off, e to the minus I omega t is kind of confusing, right? Because it's an exponential with an I. It's hard to work with. But there's one formula that you need to know that will really help simplify whenever you have e to the I something. And that's this formula. It's e to the ix is equal to cosine x plus I sine of x. Because this is nice because you can take this weird complex thing that's kind of maybe difficult to understand and split it up into just the sum of two parts, which is a real part, the part that's not multiplied by I, and then the imaginary part, which is multiplied by I. So we want to figure out what e to the minus I omega t is, so we just plug in minus omega t in for x, and so we get that e to the minus I omega t is equal to cosine omega t minus I sine of omega t. And this is a lot easier to work with because we're comfortable with sines and cosines, so what we're going to do is we're just going to plug this in to our original expression and see what we get. So if we plug this in, we get cosine omega t times f of t minus I sine of omega t f of t and integral all that. Because you distribute the f of t in. And you get these 2 points. There's one more thing we can do to kind of simplify this, make it a bit easier to understand, so we can take what we just found, and we can split this into two integrals, right? Because this is a sum within an integral, we can split it into a sum of two integrals. And if you do that, you get this. So the full thing, if you replace e to the minus I omega t, that's equivalent to this, which is actually kind of easy to understand, right? This first integral is the comparison score for the cosine version of our wave minus I times the comparison score for the sine version of our wave, right? So now we've kind of stumbled upon something interesting, right? This f of omega, when you use this e to the minus I omega t, what you really get is a sum of two comparison scores. One, when you compare with the cosine version of your wave, and another, multiplied by I, is the sine comparison score. When you compare with the sine version of your wave. So graphically it looks like this, right? The comparison score for the cosine version of the wave that you're comparing, or the frequency that you're comparing, gets put here. And then the comparison score for the sine version of your wave is multiplied by I and then put here. So this is a bit of an update. And it's interesting how you kind of do two and you add them together to get f of omega. So this is sort of an update, right? Before we just had f of omega was this constant, was this real number that was supposed to represent how much of a frequency you have within your signal. But now we have f of omega is equal to a plus bi, which is a complex number. And so now we've kind of ruined our idea. F of omega was supposed to represent, how much of a frequency we had within our signal. Now it's a complex number. What does that mean at this point, right? So we have to do a bit more analysis to figure out what's going on. But so now we have to update what f of omega means, right? It no longer really represents the frequency content of the signal so much as it's just a plus bi, where again a is the comparison score with the cosine version of the wave, and b is the comparison score of the sine version of the wave times -1. And so what does this mean? Well, if you recall, the signal that we've been working with this entire time is this formula here. I know it looks really long. It's just a bunch of sines, and it's a 0.3 hertz signal plus a 1 hertz signal plus a 1.9 hertz signal plus a 4.7 hertz signal. They're all sine waves. They all have the amplitude of 1, and they all have no phase attached to them. This is the signal that we've been seeing this entire time through all 3 levels. And so they have no phase, they have no or they have 1 amplitude. And so what I'm going to do is I'm going to shift the phase of 0.3 hertz. Okay, because what I want to see, what I'm trying to figure out is we're trying to see how does this a plus bi change, right? Because we now know f of omega is this complex number, and we want to see how does it change if we change something about our signal. And so what I'm going to do is I'm going to change the phase of 0.3 hertz, of the 0.3 hertz component of our signal, and I'm just going to shift it. I'm going to leave every other component alone, but just the 0.3 hertz component of our signal, I'm going to apply a phase shift, and I'm going to see how that changes a and b within f of omega. And so f of 0.3 is what we're going to be computing, and remember that's the comparison score with cosine of 0.3 hertz minus I times the comparison score of sine of 0.3 hertz. And if you change the phase of 0.3 hertz within your signal and you keep computing these, you get this GIF here. So let me explain what this is showing. So this here is the cosine plotted over our signal, and here is the sine plotted over our signal. You can see that the signal is shifting, right? Because again, we're shifting the phase of the 0.3 hertz component, and you can see what the phase of the 0.3 hertz component is, right? Because you can follow it with your eyes. And you can see this here is the comparison score for this, for the cosine version of the wave, and here is the comparison score for the sine version of the wave. So now we can kind of see how A is changing and B is changing, right? And we don't care about I right now because we're just computing this comparison score. And so we can see that when we're in phase, for example here, the comparison score is very high, right? It's 0.5. And here it's completely out of phase in this case, and it's negative 0.5. So everything checks out. And you can check yourself to see, does it look in phase comparison to what the actual score is. And so you can see that this kind of implies certain things, right? So notice how they don't kind of move together. And that's going to play an important role here in a second. And another thing to mention is that, why is it useful to have 2 comparison scores and then sort of add them up? And I mean, in a way, it's sort of like if you slide out of phase with the cosine, you're almost kind of sliding into phase with the sine. So it might give you some sort of, something that you can work with. And I'm going to explain that in a second. So this is how, A and B change with time. But we don't really want to see how A and B change with time. We want to see how f of omega changes with time. So we want to see how this whole sum changes. And so the question is, how do we plot f of omega? So let's do that real quick. So we have f of omega is the real part, which is the comparison score with the cosine, plus the I times the comparison score with the sine, right? A plus bi. And so the question is, how do we plot this? We want to be able to plot f of omega and see how it changes in time. Because we've seen certain things that imply that maybe we can get some useful information out of it. And so how do you plot complex numbers? Well, this should be review. The x-axis is the real axis, the y is the imaginary axis. So for example, if you wanted to plot 2, 3i, you'd go 2 on the real axis and 3 in the imaginary axis. So in reality, it's almost like I is like a placeholder for y-axis, you know what I mean? So for example, if you had a comparison score of cosine that ended up being 2, you'd go here. And if you had a comparison score of sine that was 3, you'd go up here and you'd be at A. All right, so that's how you would plot that particular situation. And so if you plot f of omega, if you change the phase of the 0.3 hertz component and plot f of omega and see how that changes with time, you get something very interesting. You get this. So this red dot is f of omega. And you can see I'm computing the 2 comparison scores here. And you can check yourself to make sure that this point is actually accurate. For example, this y component is about to go to -1, and the y component is -1. This x component, which is the real part, is about to go to 1. You can see it's about to go to 1. Right? And they hit 1 at the same time. So this comparison score with cosine is the x component of this point, and this comparison score with sine is the y component of this point. And interestingly, as you change the phase of the 0.3 hertz component, this f of omega moves around in a circle, which is very interesting. And we kind of saw this. We saw like, as one moves one way, the other moves the other way, and it kind of seemed to move in this pattern. And so first off, I want to mention something. Notice in level 2, what I defined as the comparison score f of omega, I just said the sine was f of omega, right? That's as far as I went. I just said, yeah, you just need to plot the sine wave and multiply it by f of t and then integrate, and that's it. So therefore, this comparison score would be the level 2, explanation. But notice how the amount of 0.3 hertz in our signal is not changing. It has amplitude 1, meaning if you change the phase, it's still the same amount of 0.3 hertz that you have in your signal. So changing the phase shouldn't be changing the comparison score. So this kind of shows that the level 2 explanation is really not enough, because it's changing with phase. If you're changing the phase of 0.3 hertz, you still have the same amount of 0.3 hertz in your signal. It's just you're changing the phase of it. So therefore, your comparison score should not be affected. But here, you can clearly see that it is as you change the phase, which means that the level 2 does not work out. And so now we have kind of a problem, right? So f of omega is this, but notice how, again, it's changing with the phase of the 0.3 hertz component. But again, the amount of 0.3 hertz is the same. So we have an issue here. We can't say that f of omega represents really the amount of 0.3 hertz in our signal, because it's changing and it shouldn't be. So, do we scrap this idea? No, because we need to come up with some sort of thing that is constant. So what is something in this diagram that is constant that we can now say represents the amount of frequency content of 0.3 hertz? And if you see, the one thing that's constant is the radius. The radius of the circle is constant. No matter where you are on the circle, the radius is still the same. Or I guess I should say the distance to 0 is the same. And it turns out, if we're working in the complex plane, that is the absolute value of this point. So if you take the absolute value of f of omega, it gives you this length here, which in this case is 1. And so now we can say, okay, we've kind of updated our ideas. The absolute value now gives you the frequency content of the signal, which it does. It gives you the amplitude of 0.3 hertz. And that's why in these Fourier transforms, you have an absolute value for the y-axis instead of just f of omega. Now, another thing to mention, so that's one thing. Okay, cool. We've figured out a solid way to get a frequency, content or comparison score. I'm just going to call it the amplitude at this point. We found a solid way to get the amplitude that is based on e to the I minus I omega t, and this amplitude doesn't change with phase because it's the absolute value. Another thing to mention is that notice as we're shifting the phase of 0.3 hertz, this gets a unique point on the circle within 0 to 2 pi, because 0 and 2 pi are the same, right? So as you shift from 0 to 2 pi, this 0.3 hertz component, this f of omega gets a unique point on the circle. So what does that mean? It means that given f of omega, you can figure out the phase of that component. So now we've figured out a way to find the phase of your components on top of the amplitudes. And the phase is dictated by what point you have along here. So let me show you, for example, if the f of omega was here for some sort of signal, you can figure out the phase. The phase is actually this angle here. And so you can figure that out through trigonometry, right? So remember, the x-axis is the real part and the y-axis is the complex part. So therefore, tangent of the phase is the imaginary part over the real part, or what's another way to say that? The comparison score with sine times -1 divided by the comparison score with cosine. And that gives you the tangent of the phase. So now we've come up with a lot of useful things. So this is why we use e to the minus I omega t, because if you use sine, it changes with phase, which doesn't make sense. And we can get an amplitude which doesn't change with phase, and we can also get the phase itself, the phase of your component, which is b over a. So that's why we use e to the minus I omega t, and that's why it's useful. So this is the full explanation. This is how we go from a signal in time to the frequency components that make it up. And so just to really hammer it in, what I want to do is I want to take a new signal, and we're going to compute the Fourier transform for it, by hand, doing the computation straight out using the level 3 explanation that was just given. So like, how do you do it? What's the algorithm? And so we're going to do this. So this is the signal that we're going to try to find the components of, and we're going to try to find the amplitudes and the phases. And we're going to do the level 3 explanation, level 3 way of doing it. So first thing, remember from level 1, we're going to hold up a bunch of waves, right? Still same idea. We're going to hold up a bunch of waves and compute the comparison scores for every single wave. So we could start with 0 hertz, but 0 hertz doesn't oscillate, so I'm going to start with 0.2 hertz. So 0.2 hertz, if you plot it over, you get this. And using your level 1 explanation, you'd see, it doesn't really fit. But we're on level 3, so we got to compute the comparison score using level 3. So we plot the cosine version, right? The cosine wave over. So cosine of 0.2 hertz, if you plot, it looks like this. And if you do the comparison score, so you multiply and then integrate from minus infinity to infinity, I'm going to tell you right now you get 0. So then you also have to do the sine, right? Plot the sine over, multiply, integrate from minus infinity to infinity. You also get 0. Okay? So therefore, the cosine is 0, the sine is 0. So therefore, we can conclude that f of 0.2 hertz is 0 plus 0i. And then the amplitude is the absolute value of 0, which is 0. Okay? And then the phase is irrelevant, right? Because the amplitude is 0. So therefore, we can conclude that 0.2 hertz does not contribute to your signal. And so it doesn't matter what the phase is. It doesn't contribute. Awesome. So if we have our blank Fourier transform here, the x-axis is frequency and the y-axis is amplitude, i.e. how much does this frequency contribute, we can conclude that 0.2 hertz has 0 amplitude and does not contribute at all to this signal. Awesome. All right, let's keep moving. We can't do this with just 1 point, so we have to keep going. 0.5 hertz. All right, so if you plot over, it looks like this. And using your level 1 explanation, you might say maybe. It might fit. I don't know. But again, we're on level 3, so we have to compute it out. So if we do the cosine version, plot it looks like this. Turns out if you do the integration, it's 0. And if you do the sine version, plot it, do the comparison score, again, it's also 0. So again, you have 0 and 0, so therefore f of 0.5 hertz is 0 plus 0i, and so the amplitude is 0, and therefore the phase is irrelevant. And so now we've concluded that 0.2 hertz and 0.5 hertz both do not contribute to our signal. We have ruled them out. Let's keep going. Third wave, 0.7 hertz. If you plot that over, you could say, hey, maybe it might fit, but who knows? Let's compute the scores. Do the cosine version, and look, see, it's completely out of phase. And so you get -2, which works out, right? Because remember, when you multiply these, you get a bunch of negative numbers, you're adding up a bunch of negatives, and you get -2. If you do the sine version, plot it looks like this, and you actually get 0. Okay, so we have the cosine version is -2, and the sine version is 0. So therefore, we can conclude that f of 0.7 hertz is -2 minus 0i, so just -2. And the amplitude is the absolute value, which gives us 2. And the phase is inverse tangent of 0 over -2, or minus 0 over -2. And so one thing to mention is that the inverse tangent gives you multiple angles. And I just chose the one that matches with because I already knew the answer. Because it gives you 0, 2 pi, they're the same, so it'll give you multiple answers. But negative pi is the one we're looking for, so therefore the amplitude is 2 and the phase is minus pi. So therefore we can put these things together to conclude that 2, which is the amplitude, times cosine of 2 pi times 0.7, so that's 0.7 hertz, t minus pi is one of our components. We have found this is a component of our signal. Awesome, okay. So now we can plot that on our Fourier transform, so we know that 0.2 and 0.5 hertz are both 0, but then the amplitude of 0.7 hertz is 2. Awesome. So let's keep going, and I think you guys are getting bored at this point, so I'm going to speed it up a little bit. So if you want to do 1 hertz, you'll find out that both the cosine and the sine versions are 0, so therefore the amplitude is 0, and so we plot 0 here. And then we do 1.3 hertz. If you plot it, it looks like this, and therefore the cosine is 0, and the sine ends up being 1. Which means that this is correlated. So therefore, the amplitude is 1, and the phase ends up being pi over 2. So therefore, we can conclude that cosine, which is amplitude of 1, times 2 pi times 1.3t plus pi over 2 is another component. And so I'm not going to torture you anymore. Here's the Fourier transform. We've computed a total of 5 points. And we've found 2 peaks. One at 0.7 hertz and one at 1.3 hertz. I'm not going to torture you anymore. This was our signal that we've been testing, and turns out if you add up the 2 components that we have found so far, you actually get the same thing, which means that our signal only contains 2 components, and we have already found both of them. It's a 0.7 hertz signal with amplitude 2 and phase minus pi, and a 1.3 hertz signal with 1 amplitude and pi over 2 phase. So we have now found, given this random signal, we have found the components and the amplitudes of the components and the phases of the components using our level 3 explanation, which was extremely useful. And we've also computed the Fourier transform, right? We've at least 5 points of it, but if you actually use MATLAB to plot out the real Fourier transform, it looks like this. And notice how we got it right? We found 0.2 is 0, 0.5 is 0, 0.7 is 2, 1.3 is 1, right? And so this is what MATLAB does, is it computes a bunch of these points and then it just connects them with straight lines. And so you can see that we matched the Fourier transform quite well. And so that has been the level 3 explanation of the Fourier transform. We definitely invite you to watch the other videos. And again, if you want to share this with a colleague, we have no problem with that. And I appreciate this. I hope this has been useful for you, and thanks for watching.